Okay, so I want to talk now. This is the third lecture, so lecture 3, and we're still on chapter 1.1, I think. We're just finishing it. Um, now I want to talk about what spans are possible in R3 and Rn. Let's think about R3. So let's write this down. What spans are possible in R3? So for 3 vectors, say I have u, v, w in R3. Okay. So u equals u1, u2, u3, like this. All right, etc. Okay, so what kind of spans can we get? Well, if all 3 are 0, we get 0. So first one is 0 is possible. If, only if and only if all 3 u equals v equals w equals the 0 vector. Okay, any combinations just gives me this. 2, a line, right? A line is possible. A line is possible. It's not a lime. A line is possible. So this happens if one of them, at least one, u or v or w, is not the 0 vector, and they're multiples of each other. So say, let's just write they are multiples of each other. So this should be clear, right? Because say, example, suppose u equals 1, 2, 3, v equals -1, -2, -3, and say w equals 17, 34, and 51. Okay, then any linear combination is going to be a multiple of these, right? So any linear combination can be written. So then cu plus dv plus ew can be written as some, say, c prime u. Okay. All right. In fact, you could even figure out what c prime is based on these, right? C prime should be, well, this, it's going to be c minus d plus 3e, right? Right? So this is equal to c minus d plus 3e u. Okay, so everything can be written as a multiple of u, so it's just a line. All right, what about 4? Three, let's do 3. If, now here's the, this is the one. So if I can write one of the vectors as a combination of the other 2, but I can't write all 3, all 3 are not multiples of the same vector, then I get something that doesn't fill the whole space, but just fills out a plane. So if one vector, actually could be any one, I think, any one, if one vector, say w, is an LC of uv, i.e. w is contained in the span of U and V, right? Then if U and V are not multiples of each other, the span of U, V, W is a plane. Okay? So in this case, you have a plane in R3. So can you see a plane in R3 in your head? This is what it is. Okay, it's the span of two vectors in R3, and the third adds nothing. The third adds nothing. It just lands in the plane as well. So drawing these is never fun for me. I'm not a talented three-dimensional artist, but which means I don't enjoy it either. So, but the idea is, if I just try for your sake, I have three, right? And I have another one here, and these you know, go and make a plane, right? And then I have a third one, and they're all in the same plane. So U, V, W lie in same plane. Okay, so this happens when one of the vectors, or any one probably, is in the span of the other two. Okay, so let's do a little, give a numeric example of this probably. So suppose I have U equals, let's pick something not too hard here. So how about U equals 1, 1, 1, 0, and say V equals 1, 0, 0, and say W equals 2, 0, 0, like that. Sorry, the order there like that, but that should work, okay? You see the thing here? Everything lies in the XY plane, right? Even though the space is R3. This is not such an, I like these ones, are more interesting, the ones that are not in a coordinate plane, but this one's okay. So this is the whole, so span UVW is equal to XY plane. Right? Right. So you can see this graphically. Maybe this is the x-axis here. So there's V. U would come out here. And can I make W? Say W's over here with these two? Yes, you can, right? You would extend out here more and then project, and then take a negative of this one to get back to here or something like that. So they're all in the same plane. Okay. You could do other ones. They don't have to lie in a coordinate plane like this. Okay, so. All right. Finally, the fourth one. If now the word here is independent. So if the three vectors are independent, which means there is no multiple of any combination of the other ones that will give me one of them, then we get the whole space. So so let's say if let's not play here. So like let's say if U, V, W are independent, and this means no multiples of any one or two can give me the other. I'll define this below. Then the span is the whole plane. So definition. So let's now, sorry to abuse this notation in a second way. So suppose I have k vectors in Rn, and we say, so let those be in Rn, we say the set is independent if and only if C1, V1, CK, VK equals the zero vector when C1 equals C2 equals ... equals CK equals 0. So you can see this means they're independent, because otherwise there would be a way, if there was some non-zero set of C's here, I could add it over here, and I would have a combination of, I could add one of the non-zero C vectors over here to the zero side, and I would have some combination left on the left side that would equal the vector on the right. I'll do this a little more carefully when we get to chapter 2, but there's no point in holding back. You need to learn this stuff, so there we go. That's the end of the apology for that. Okay, very good. So that's the end of chapter 1.1. The next set of lectures, which should be coming, we'll start with 1.2 on length and dot product and orthogonality. And then we go to matrices. So expect about, I don't know, 4 or 5 or 6 more for the rest of chapter 1. Okay, thank you.